Hey everybody, welcome back. So last week we looked at two rather different things, modular arithmetic and symmetries of a square. Those two settings had some similarities. In particular, in both of them, we were able to make some sort of a table, right? We made the addition table for addition modulo 4 on worksheet 2 on Wednesday. We made the composition table for symmetries of a square on worksheet 3 on Friday. And the fact that we could make a table like that reflects that in both of these two settings, we had some way of combining two things to produce a new thing. It was addition in one case and composition in the other. So our goal for today is to generalize those into a more general notion called a group, which is going to wind up being the primary object of study in this course. The rough idea is that a group will be a set with an operation on it. The operation could be something like plus, or times, or composition, and I'll also require that operation to satisfy some conditions or axioms. So in order to make this rough idea precise, the first step is for me to tell you more precisely what I mean by this word operation. The more technical name for this is a binary operation. Here's the precise definition. Let's let G be any set. Then by a binary operation on G, what I mean in mathematical notation is a function from the product G cross G to G. That's a little bit hard to parse, but in words, what this is saying is that a binary operation takes in two elements of G and spits out one element. Or in other words, it's a way of combining two elements to produce just one. Here's some examples. Plus is an example of a binary operation on the set Z of integers. I'll use that notation Z throughout this class, by the way, to denote the set of integers, otherwise known as whole numbers. The reason plus is a binary operation on this set is that plus is a way of taking in two integers, like maybe 3 and 7, and combining them to produce a single new integer, in that case, 10. Times is also a binary operation on Z, because if you give me two integers, another way I can combine them to produce a new integer is to multiply them. Plus modulo n is a binary operation on the set Zn. That's a rephrasing of what we saw at the end of Wednesday's class. If you give me two elements of Zn, like let's say Z4, for example, which is the set 0, 1, 2, 3, then I can add them, modulo n, so modulo 4 in that case, to produce a new element of that same set. And one last example to tie this back to the things we saw last week is that composition is a binary operation on the set of all symmetries of a square, because we can take two symmetries of the square and compose them to produce a new symmetry of the square. Before we keep going, I think it's helpful to have at least one non-example. So for a non-example, division is not a binary operation on the set of integers. And why not? Well, there's actually two different reasons. One reason that it fails to be a binary operation is that if I combine two integers with division, the result is not necessarily an element of the integers. For example, if I start from 5 and 2, which are both integers, if I combine them using division, 5 divided by 2 is not a whole number, so that's not an element of the set Z. The mathematical terminology we'll use for this phenomenon, by the way, is we'll say that Z isn't closed under division. Again, that means that I could start from two elements of Z, but when I combine them under division, the result may or may not still be in Z. And then the second reason, by the way, that division is not a binary operation on Z is that it's not defined for all pairs of integers. For example, if I try to take the pair of integers 5 and 0 and divide them, then that's not something that I have an answer for. In order to be a binary operation, I have to have a way to combine every pair of inputs and produce some output. Okay, so with these foundations about binary operations in place, we're ready for the moment of truth, the definition that's really going to form the foundation of our study of abstract algebra, the definition of a group. So a group is defined as a set G together with a binary operation on G. I'm going to call that binary operation star for now to remind myself that it might be plus, it might be times, it might be composition, it might be something weirder that we haven't even thought of yet. So I'm just going to denote it by this symbol star. And now I'm going to require that this set with its binary operation satisfies 3 properties or axioms. The first property is that I want star to be associative. What that means is that if I take 3 elements, A, B, and C, in the set G, if I combine A and B with the binary operation and then combine the result with C, that's the same thing as if I take A and combine it with the quantity B star C. And this is going to be true, I want to require this to be true, for all elements A, B, and C in the group. The second axiom I'll require is that star has what's called an identity element. What that means is that there exists some element, which I'm going to denote by E, and that element, if I were to combine it with anything else under the binary operation, it wouldn't do anything. I'd get back the thing I started with. In symbols, what I'm saying is that if I do A star E, I'll just get A back. And if I do E star A, I'll still get A back. And that's true regardless of which A I started with. The third and final condition I'll require is that every element of G should have an inverse. What that means is that for all A in G, there exists some other element of G, which I'll denote with this A to the minus 1, and I'll call that in words A inverse, or the inverse of A. And that's an element such that if I do A star A inverse, I get the identity. And also, if I do A inverse star A, I'll get the identity. If you think back to your experience from linear algebra with matrices, this might feel a little bit familiar. Remember, if you multiply a matrix by its inverse, you get the identity matrix. Similar idea here. I know the definition of a group is a lot to take in on a first pass, but let's start by looking at an example, which I would think in some sense, I'd think of this as the prototypical example of a group. And that's that we could let G be Z, remember that's the set of integers or whole numbers, and then we could let star be the binary operation of addition. So I claim that this is a group, and if I want to be sure of that, I should check to make sure it satisfies those 3 axioms. Actually, to get us in good habits for later, I want to even take this first opportunity to say that when I'm checking that something's a group, I like to actually think of it as checking 4 things, which I call thing 0, thing 1, thing 2, and thing 3. Things 1, 2, and 3 are the 3 axioms that we saw on the previous slide. Groups have to be associative, have to have an identity, and have to have inverses. But even before getting to those, I like to check thing 0, which is closure, because that's what we would need to check in order to know that star is a binary operation at all, which is also part of the definition of being a group. Remember what closure, or being closed, means. It means that if you take two integers and combine them under the operation, so in this case plus, if you add two integers, then you get an integer. That's true, and so z is closed under plus. That tells me that plus really is a binary operation on z, as we saw earlier. Checking that plus is associative amounts to checking that this equation here is true for all a, b, and c in the integers, and that's indeed true of the integers. Actually, perhaps in your Math 301 course or in another previous course, you might have carefully developed the axioms of the integers, in which case I bet this associativity was one of them. But in any case, for our purposes, let me assert that that's something that's true of addition of integers. How about the identity element? Remember what that should be is something that if I combine it with anything else, I get that thing back again. And in this context, combine means add. I'm looking for a number that if I were to add it to any other integer, I'd just get that integer back again. In this case, that identity element, e, is the number 0. Because if I were to do a plus 0, I'd still get a. Or if I were to do 0 plus a, I'd still get a, for any integer a. So I've found an identity element that checks that axiom. And the last axiom is about inverses. The inverse of an integer a should be an integer that I can add to a and get the identity, which we now know is 0. What could I add to a to get 0? Well, the answer is negative a. So every integer has an inverse, namely it's negative, so that checks the third and final axiom. We've confirmed that the integers with the operation of addition are indeed a group. The same basic idea actually gives us a whole bunch of other examples. Like, for instance, I could take G to be the set Q. That denotes the rational numbers, otherwise known as fractions, one integer divided by another. And then if I still take my operation to be plus, essentially the same exact argument we made shows that this is a group too. Or similarly, instead, I could take G to be the set of all real numbers, which I'll denote by R. And again, with star being the operation of plus, the same argument shows that this forms a group. Or I could even take G to be the complex numbers C and still keep the operation as plus. So those are our first few examples of groups. There's lots more for us to meet, which we'll start thinking about in our worksheet for today, but that's enough for this video, so I'll see you in class.